2b part 2 is about potential, which you are familiar, but we will go through it with the vector calculus as our tool. Now let me introduce and motivate it by asking you to give me an electrostatic field which somehow gives me E magnitude of x but in y direction. Now, can you produce this field in the lab with all the resources in your command? You can ask for any amount of batteries, conductors, charges, capacitors, what have you. Can you produce this field? Before proceeding to produce this, maybe you should sketch it. And then probably you will realize what you are up against. There is another way to figure out. That is, take the curl. Okay? And we know, and we are going to show, that E field cannot be curly. Never, if it is electrostatics. And if it is curly, then no matter how much you try to arrange things, charges, you will not be able to produce an electric field. So let's compute the curl of this. It's Cartesian coordinates, I, j, k, del by del x, del by del y, del z. The only component that survives is y, the other two are 0. So the only component that survives is k, del by del x of dou by dou x of x minus 0, and that is k, which means it has a non-zero curl, and hence it cannot be electric field. Let's show that. Okay, why is it that electrostatic field is curlless? Let's consider the field due to a point charge, and we know that 1 by 4 pi epsilon naught q by r square r hat. It is a spherical symmetric, so I can now use the curl, okay, of spherical symmetric. Okay, so r, you remember the weights, r theta prime, r sin theta phi, and the only component here is there of r is er. And then if we just compute it, del by del theta is 0, everything else is 0, so it is 0. So you can see that if any electric field, or in fact for that matter any vector function which is directed at r and has only an r component, the curl will be 0. So this is something that you have studied in the last course, okay, that any function that is central, okay, what is AR R type, central meaning its magnitude depends only on R and it's directed along R, depends on R and directed along R, its curl would be 0. And that is what you actually talked about in the last course as conservative forces. Here we're talking about vector function. Okay, so if it is of one charge, the curl is 0, then it will be, curl will be 0 for all superpositions. E can be due to superposition of qi or dq, and hence curl is going to be 0. I'm just using the superposition. But you can say that I know of E which depends on r, theta and phi. For example, you might have seen the example of dipoles, okay, which has both r and theta components. Sure, you can have r, theta, pi components, but in such a way that del cross is 0. That's a condition still. You can have many components by arranging things. The restrictions that these three would be followed. That is del by del theta of E phi in such a way. So these are just the conditions. I have derived it from the curl. Each component of the curl must be 0, and hence it puts restriction on these three conditions. So you can have r theta phi component provided, okay, you have satisfied these conditions, which ensures that curl is 0. Or in Cartesian coordinates, okay, this is each of these components, okay, should be such that del y by del x must be del x by del y, and so on and so forth. Okay. So these are precisely the conditions for del cross E is equal to 0. Now, let me give an advance alert that this is del cross E is not 0 in electrodynamics. This is only true for electrostatics. Later we'll see there will be another component here, okay, which is time dependent, and hence it talks about electrodynamics. Since del cross is 0, we have already seen in our last chapter there exists a scalar field, let's say V, such that del cross, because this is identically 0, this is a math identity. So if del cross E is 0, I should be able to write E in terms of a gradient of a scalar field, and I call it, let's say, del cross V, and this is an identity, and hence that exists. Let me now construct. Okay, so if this exists, let us now construct an appropriate V for E. All right, so what's are the hints that I should take for this construction? I know del cross E is 0, which we have seen even in the last chapter implies and is implied by that if I take E dot dl, which is something like if E were a force, then it's like work done from A to B, is independent of paths from A to B. From 2 points A to B, you could take any, and it will be independent of path if there is no curl. That's something that we have proven even last chapter. And if you take it across a whole path, then of course it's 0. If it's independent of path, if A and B close on each other, it will be 0. So that is, we'll take it as the hint. Okay, so inspired by the work done by a test charge in going against the field, we define, okay, the V at any point R, this is scalar, this is the position where you are calculating the scalar, is defined by minus some reference, some convenient reference to the point R where you want to calculate, just E dot dl. It's where this is some reference point. This minus, of course, is inspired by the test charge going against the field. I'll say more about it later. And that the reference point really does not matter, because mostly what we're interested in is a potential difference. That is V, point B, could be vector point, minus VA. So take from the reference point, okay, and to B, and then reference point to A, okay, minus of that. And what is that? That is basically O to B and A to O, okay, which means this is minus A to B E dot dl, the path difference. It is simple. But we know this now. This is 2 edges is equal to E dot dl. This is a line integral and is equal to E dot dl. So the fundamental theorem now will invoke. What it says is, if the 2 edges and this path independent, this must be the grad of V dot dl. That is what the fundamental theorem has told us. Okay, and hence I'll see that grad dot V dot dl is nothing but minus E dot dl. But this is true for any 2 points A and B. Okay, and hence I can say that E must be minus, since it is true for any 2 points, E must be minus grad of V. So as promised, E is the gradient of V that we have constructed. So we have constructed the voltage function, scalar potential, and we show that the electric field is minus grad of V. Okay. Now let me go through some comments. I'll call it as if running through a FAQ on potential, frequently asked question on potential in that format. So why so much of hoopla over potential? Who said hoopla? Because yes, the whole electrostatics is indeed a potential theory. Because life will be easy to calculate E from a scalar function just by differentiating, such that we'd have no messy vector integrations with 3 components. But then you may ask, how is it that a single scalar function has all the information about a 3-component vector function? Good question. It is because there are 3 restrictions or constraints on E coming from del cross E is equal to 0. Just to remind you. Okay, so a scalar function is able to do the job of a vector function because we have specifically imposed the 3 conditions coming from del cross E is equal to 0. All right, so the whole electrostatics becomes, in my opinion, a beautiful potential theory if you can do that. So now, what's in a name? There is a possibility of confusion between potential and potential energy. Some students even think that it is meant to confuse students. Sure, potential is related to potential energy, but it is not potential energy, because we are going to now consider potential energy in the next section, in the next lecture. To distinguish, sometimes people call this as electrostatic potential, but we'll just refer to as potential, or even just scalar potential. Why scalar potential? Because we are going to soon meet another field in which we'll have a vector potential. Okay, this is an advanced alert. So that is why, to distinguish, sometimes people call it as the scalar potential, that is electrostatic potential. I've just referred to it. Why introduce a minus sign? Well, the inspiration comes from the work done against the field. The conventional idea that the plus charge should be at a higher potential, hill, okay, and the minus charge in a valley. That is the basis. So we want to make the potential as plus around a plus. That is, if I have a test charge, I have to climb up the hill. Whereas if I have a test charge with a minus, it will just drop off because it's attracting. All right. So field at test charge goes downhill like water in gravity. Okay. And test charge repelled from plus charge. So need to do work to climb. Okay. But gets attracted to minus. So that is the convention that we are following to introduce that minus sign. Add or subtract a constant. Should it matter? No, it should not matter for potential. Why? Because if, let's say, another potential which has a constant, C is a constant, then the grad is, because we can measure only electric field. So electric field is grad. So that doesn't matter C. But let me give you an advanced alert. This may look trivial, but has deep consequences in the structure of the theory. And it's called gauge invariance. I'll be discussing that later when we discuss Maxwell's equations. Is superposition valid for potential? Absolutely. Since it is linear in charge. So if I have calculated potential due to rho 1 and separately calculated potential for rho 2, then if they are taken together, I can just add V1 plus V2. So E obeys superposition. So does the scalar potential. Okay. So if there is a vector sum of E, then this is the ordinary sum of potentials. Okay. It will correspond to. So superposition is valid. That's an added advantage. It's just an ordinary sum once you get potential. Now, where is the reference? Of course, reference is your convenience. For localized charges, normally as r tends to infinity, we take tending to 0. That's a good choice. But there are some charges which are going to infinity, like a line charge or a surface infinite plane of surface charge. A better choice is required. Okay. For most practical problems, though, Earth is a good choice. Okay. This is called ground. So adding or subtracting charges to the ground does not change its potential because it's a huge bank of charges. Okay. But to get a good ground in the lab, we spend a lot of money. Okay. We brine solution and very thick copper wires are required, essential in my lab, because if I don't have an earth or a good ground, then my noise levels that I measure, I want it to be in microvolts. That will not happen. Okay. In the house, if you have a solar panel or something, okay, and if you don't have a good ground or in any house supply, you can get yourself electrocuted. Okay. So a lot of money is actually spent in creating a good ground as the Earth's reference. Now, what are the units? We know the volt, Newton meter per coulomb or joule per coulomb. And this is one of the most used units because every signal ultimately that has to be electronically processed, for example, in your cell phone, okay, whether it's pressure, temperature is converted into volts. And then to display also, you require signals in volts. The volt is actually, this is so easily measured, we don't normally measure electric field. We measure potential, okay, and then express electric field in terms of volt per meter. Okay, so all the signals or sensor in your mobile, for example, have to be finally be converted into an electrical signal and measured in terms of volts. So let me come to brief discussion on standard cases, which you know, but I'll just point out. Okay, so what is the point charge potential? That is, if I start from infinity to r, at any point r that I want my potential, my electric field, okay, and dl, I just take the most convenient path because it's path independent, and along the r. So that is, of course, we know q 4 pi epsilon naught r. So if you have a positive charge, it goes by 1 by r. If you have negative charge, it goes by 1 by r like that, minus q. Okay, so it is spherically symmetric, and hence I can take my dl like that. Okay, as soon as spherically symmetric, if you have to find a E dot dl, you can always take this path, the easiest path, because that is the easiest path. This is path independent. So this is for a point charge. What about bunch of charges? I will just superpose qi by ri. Okay. Now this ri is the field and source separation point. Now if there are continuous charge distributions, instead of q, I have dq by r and integrate over wherever I have. Okay. I'm assuming that this integration is over a charge distribution which is localized. Okay, so if it is line charge, then of course dq is lambda r prime wherever the source is. There is the integration only over the sources. Okay, del r by r is the field point, or sigma r dA or rho d tau. So this translates to either lambda, sigma, rho, or a summation of q, or even combinations of them. So if it is easy, if E is easy to calculate, then of course VR is minus E dot dl. So you know E, and hence you can calculate. That's the best way to do that. Okay. But sometimes it is a lot more directly to obtain from charges. If your integration over charges is convenient, then we can get V of R dq by R, okay, and then obtain E is minus grad of V. Okay, this is simple. Now let's take the case of a long line charge. Okay, so of lambda, this is a long line charge. Long means infinite basically. So this is a case where we can easily find out E and then convert it to V. We already know E from Gauss's law. E lambda 2 pi L naught S. S is the cylindrical coordinate. It points in the S hat direction. Okay, and the path that I take is so this is S hat direction, and dl, the path that I take is ds s. This is the most convenient path. Okay, so I obtain the potential as log of, since now this is since a log, I can take a convenient where S is equal to S naught as the convenient reference where ln1, that becomes 0. Okay, so there is a cylindrical symmetry, and I can take S naught as a cylinder at arbitrary reference at S naught such that it is 0 at that. In practice, in the lab, what we do is put up a very huge coaxial cylinder with large dia maintained at V naught or sometimes ground as the purpose in the reference in the lab. This configuration is very often used in the lab. Suppose you have a finite length lambda. Can you do this? Okay, of course you can do that. Suppose there's a finite length lambda, I want my potential here. Okay, so which method is better? You cannot use Gauss's law. It doesn't have the required symmetry, and hence in this case dq by R is the most important. You can get E from Coulomb's law and then calculate V, but you can directly integrate over this lambda to obtain the potential at point P. Try that as a task. So let's take up a example, a popular example, that is a ring of charge, which is, let's say, I want Vz on axis, a ring of, let's say, radius R and uniform lambda. Okay, this is a simple case. This we have already, you might have done for E, but you can do it. Charge method is a lot more convenient here because from the point, all the charges are at the same distance. There is no really integration involved. So V of Z, okay, at point P is a total charge Q summation divided by 4 pi epsilon naught, and the distance R square plus Z square. This is R and R square plus Z square. And all the charges are at the same distance. And hence, we can just directly write it down, where I've written down Q as, of course, 2 pi R lambda, the full Q. And then I can obtain E minus grad V, and that is simple because there is only del Vz by del Z, and it will be pointing in the K direction. Okay, and that's, so instead of Coulomb's law, doing it to the charge and charge directly to potential is a lot more easier, and in fact, you can get E a lot more easily. Okay, so then K is in this direction. Let's plot this Vz and Ez. Okay, so what would be the V of Z? Let's plot that. So this would be something like that. Okay, so we have already gotten V upstairs here. Let's Vz. It is R square plus Z square. So we can always plot it. Let me choose this. So it goes down like that. Wait. Symmetric, of course. I have not drawn that symmetric. And so Ez, and you can plot Ez, that is Vz. This is minus del Vz by Z. So slope is positive here. So it will become negative. So let me plot it as This will be negative, there will be peak, it will go through 0 peak, and then like that. So it is peaking around r by root 2, and here also r by root 2, and the field goes to 0 as in the center. This is an important activity in doing plotting to get an idea of the field and the potential. You can take Ez as minus del B by del Zk, and that will be that. Okay, Q, but is this true? Can this be true? There is an important difference. You cannot obtain the electric field just by knowing the V on the Z, because here the symmetry is not helping us. So there in the full ring, I was sure that the E was in the Z direction, and hence I could differentiate. There was no field, no component here. I cannot say that there are no components. Hence, to be able to obtain, first you have to obtain for a general point, then take the grad, and then take Z is equal to 0. Okay, so this is the point that I wanted to illustrate by taking this example. Of course, we can do from Coulomb's law, okay, the E, okay, and then exactly the way I did for E cos phi, you could do that, okay, so there will be a sine alpha component, this is the alpha, and then integrate over it, and then you'll see that indeed develops not only a Z component, okay, but also a minus I component. So just by looking at V as a function of Z on the axis, okay, by this calculation, you cannot get E. So typically, because of this, you need to get the V for any arbitrary point, then calculate grad, and then see for any specific direction or point. Okay, so that's the point that I wanted to make. So this is why the potential formulation does not work in this particular case. Okay, so let's take another example. Potential charge, we have already done this. Okay, so but the potential formulation is as easy. I want this is a charged disk of sigma, and I want on the axis at a point P the potential. So this is very symmetric. So I can take at any r, all the charges at that 2 pi r dr would be subtending the same potential. So I take sigma 2 pi s ds. This is for this. This is a dq, 4 pi epsilon naught, and s square plus z square, or z square plus s square. Okay, and then I integrate from 0 to r. So simple. All right, and this turns out to be sigma by 2 epsilon naught r square plus z square. If it is more than z, then of course minus z, and if it is z is less than 0, negative, then it is plus z. Okay, negative. So how do I plot that? Okay, here look at this. V is continuous. In fact, that's a boundary condition that we'll study about. V is continuous. Okay, but the slope is not. And what is the center? Is sigma r by 2 epsilon naught. In fact, you might have earlier found out what is the is the center and the edge has the same voltage? No. Okay, you can actually calculate what is the potential of the edge of this disk. But at the moment, we are going along this. This is the center. Center is, okay, of course, the highest, and then it falls off. It falls off. Okay, so that is V of Z. And then what will be E of Z? Okay, so that's the slope. In this case, the symmetry is still valid. And note that this slope and this slope, there is a jump. And you can see that the jump is here, it is minus sigma by 2 epsilon naught and then drops up. That's the field in the Z direction. And so the jump is minus sigma by 2 epsilon naught to sigma by 2 epsilon naught. The total jump is sigma by epsilon naught. This is characteristic of any time the normal component of the electric field goes through a surface charge, as we'll see later. All right, let me take the standard case of an uniformly charged sphere, which is, let's say, radius r and a uniformly charged VR, and you want the potential V as a function of r. Now, it is very easy to do this using the field from Gauss's law, because it's such a nice symmetric object. But I want to do this directly from charge. Okay, so what do is, without loss of generality, I take the point of my interest P on the z-axis. I can always orient my sphere such that my point P, this being spherically symmetric, on the z-axis. Okay, such that I can use my standard symbols, all right, of spherical coordinate system. Okay, then it's a very simple integral. So this is dq by r. So rho d tau. D tau is r square sine theta dr d theta d phi. We have written this now enough number of times. And this is r. This r is z square plus r square minus 2rz cos theta. This is such a nice integral because the integrand has cos theta, and upstairs we have sine theta d theta. So it's a very easy integral to do. Okay, so let me directly go to the result. So V, r square sine theta d theta. Of course, the phi integral is simple. That just gives me 2 pi. The theta integral is sine theta d theta z square r square minus 2rz cos theta. Since it is sine theta d theta, it is very easy, 1 by rz. Okay, so I can say r square plus z square minus 2rz cos theta, 0 to phi. And then I plug in the limits. Okay, that makes it simple. And so this becomes r plus z minus plus. I take minus for if r is less than z, and plus if r is greater than z. This is minus plus. And then simplifying 2 by z if r is less than z, and 2 by r if r is less than z. This is just the integral of this sine theta d theta. We still have to do the r integral. All right. So after doing that, we do the r integral. R integral is from 0 to z and from z to r. We have for the full charge. So 0 to z, it is less than, and hence it is 2 by z. And this 2 I have taken out, 1 by z, 1 by r square dr. Simple integral. So 0 by epsilon naught, this is z 1 by z cubed by 3, r square minus z square by 2. So this is indeed rho by 2 epsilon naught r square minus z square by 3. Now I can express it in terms of the total q, because q is rho 4 pi by 3 r cube. So v of z is, so it cancels, right? That is how. So 1 by 2 epsilon naught, I re-express this in terms of q, 3q by 4 pi r square minus z square by 3. This is more conveniently written. In fact, this is a result which is worth remembering in its form. Not the formula, but it's in form. So q by 8 pi, there is a mistake here. Let me correct this mistake. While writing, this is 8 pi epsilon naught r and 3 minus r square by r. Okay, this is the potential of a uniformly charged sphere with total charge q. What I was illustrating was what we have obtained is from just a simple integral directly from the dq by r. Okay, and then integrating over the variables d theta d phi. So we'll have some problems in the home assignment on this, so please go through that. But let me point out that is there a direct way to give given V, how do I get rho? Or given a differential equation of V and boundary conditions, how to get V? In fact, one of the central tasks of electrostatics is actually just this. Okay, so now we know E is minus grad of V. Divergence of E is rho by epsilon naught. That rho is the source of E, and divergence of E tell me about the sources. And you know that it cannot be curly, so del cross E is 0. So all these three we have gotten. So now I can plug in the divergence of E, but E is minus grad of V, and that is nothing but minus the Laplacian of V, del square of V. We have done that in the last chapter. And hence, I can write down, in fact, all of electrostatics in one form. And that is why this is called Poisson equation. Okay, del square V is equal to minus rho by epsilon naught. Now, if you know V, if you take del square, you will get rho. You will get the sources. More often than not, one has to solve for V from their E. So rho is given, and this differential equation is given. Okay. For example, Cartesian coordinate, it's simply del square V by del x square plus del square V by del y square plus del square V by del z square is equal to this. Now we have to solve this along with the given boundary conditions to get V. In fact, most of electrostatics problems in advanced courses boils down to learning how to solve this differential equation to get V. And once I get V, I can get everything else like E and charges, the boundaries and everything. Now there can be regions where there is no rho, and that is also an important condition. That's del square V is equal to 0. There are no charges. All right, and then del square V is equal to 0, and that's called Laplace equation. That's just a special case of Poisson equation. So there may be charges at the boundary, though. So given the boundary condition and del square by V is equal to 0, our aim is to solve this. Okay, so in some sense, all of electrostatics can be reduced to solving these equations given rho and boundary conditions. Okay, so we'll talk about Laplace equation in the next chapter in a great deal. We'll avoid maths, but we'll talk about the conceptual foundations of what does Laplace equation tells us about the physics of the problems in a little bit more detail. Now the question that we are dealt with, how much does E change across sigma? Okay, I have pointed out that whenever there is a surface charge, E makes a jump. Okay, we can actually prove that. Suppose there is a surface, and it is it has sigma charge on it. Okay, so what we can do is we can take a incredibly thin Gaussian pillbox such that it is just above this surface, and just below this surface, this epsilon almost goes to 0. And let's say, since it is a surface, just above it, it will be perpendicular. The E component, which is perpendicular, we'll call it above, and just below, we'll call it the E, this is below and is also perpendicular. All right. So now we can use Gauss's law for this pillbox. So there'll be the side ones will not contribute anything. Okay, but there is some charge here. So E dot dA is Q enclosed. Q enclosed is nothing but if the area is A, then sigma A by epsilon naught. All right. So since the sides do not contribute anything, so it must be, all the contribution must be coming from E above here and E below here. So E above perpendicular minus E below perpendicular must be equal to, okay, the area have been cancelled out, sigma by epsilon naught. That's a simple proof that any time if you have a surface charge and there is a normal component of electric field you calculate just below and just above, it must follow this discontinuity by sigma by epsilon naught. It doesn't depend upon the shape or whatever. All right. So this goes by. Of course, if there is no charge, then of course sigma is 0 and is continuous. Okay, if there is no surface charge, okay, there is no charge on the surface, there is a boundary, but there is no charge, then the E above and E below must be continuous. E above, but this is the normal component we're talking about. How about, so this is a general, very general result. Let me state it. The normal component of E is discontinuous by an amount sigma by epsilon naught at any boundary. I'm saying any boundary because if sigma is 0, then of course E perpendicular is continuous. It's very useful in solving problems or visualizing because most of the problems actually lies at the boundary. What about the tangential component? Okay, the tangential component of E, consider the extremely thin rectangular. Let me consider this time I take a loop, okay, in which it is just above and just below with the side epsilon almost going to 0. Okay, and I want to figure out what is the parallel component of E above and E below. All right, so quite clearly if I take a E dot dl, okay, then since this epsilon is going to almost 0, there is no contribution from the edges. All right, but we know that E dot dl is equal to 0. This is a closed path. Okay, and hence E above, if suppose there's a length L, suppose length L, then this is length L and this is length L, then E parallel above into L minus E below L, if I'm going it like this, must be 0, which means E parallel component, that the tangential component above and tangential component below must be equal. Okay, so and the combined boundary condition then, okay, can become, because the tangential component is always equal, the normal component can go through a jump of sigma by epsilon naught. So combined boundary condition is E above minus E below sigma by epsilon naught. This jump is only in the normal component and hence normal to the surface n hat. So combined boundary condition. So boundary conditions are extremely important in solving some of the problems. Now, is there a boundary condition for potential also? That's for the field. You already might have guessed from our examples that the V above and V below is continuous. Why? Because this is, let's say, A to B, just below and just above, and I can always take this path or length going to 0, which means A to B E dot dl can go to 0. So V above must be equal to V below. So potential is, even if there is a sigma, potential is continuous across a boundary of or having a surface charge. However, we know that E is discontinuous, which means that the grad above and minus grad V below is minus sigma by epsilon naught n. Okay, and so this can be written down as delta V above in the normal direction. Okay, in the normal direction to the surface, minus delta V below delta n is minus sigma by epsilon naught. Okay, what is this quantity? Delta V above by delta n, that is nothing but grad V taken in the dotted with the n direction. That is what is delta V, any of this delta V by delta n mean. All right, so that undergoes a minus sigma by epsilon naught. Okay, so this is nothing but a normal derivative of V, that is the rate of change which is perpendicular to the surface. Okay, however, it is important not to forget that the above and below we are talking about are limiting cases. Just above and just below is continuity across the surface alone. I cannot say if I go any further from the surface. Okay, so with that, let me come to the almost the whole free space electrostatics we can now summarize. That is, in electrostatics, we are given rho. If a given rho, I should be able to find out E, or given E, I should be able to find out rho. Okay, by rho, I mean all kinds of charges. It could be discrete charges, it could be line charge, it could be surface charge, it could be volume charge. I can always express it as a rho, all right? Or rho, from rho I can get V, the potential, and from the potential I can get E. So essentially, knowing I should be able to convert given to rho to V, V to E, E to rho, and so on and so forth. So that summarizes all our equations we have developed in this chapter, okay, so far. That is, E of R is, of course, rho of R by R square d tau. Okay, so this is that curly R. I don't know why it has not come out here, but clearly this should be the curly R. Divergence of E is, of course, rho by epsilon naught. Okay, and curl of E is 0. That's the relation. In fact, the inner triangle are all differential and the outer triangle relations are integral. So between rho and V, this is the Poisson equation. Del square V is minus rho by epsilon. Okay, and the integral is, if I know rho prime, okay, then this is curly R. I don't know, it does not come out properly here. Curly R d tau prime. And if I know V, I can calculate electric field simply by differentiating minus grad V. Or if I know E, then of course it is an integral minus E dot dl with some reference to wherever I want E dot dl. So all these, the whole chapter was actually based on developing this set of electrostatic equations and show its use for some of the examples and such that the meaning of these equations come out. And of course, along with that, we had boundary conditions just in the last couple of minutes, that across a sigma surface, E tangential is always continuous across a boundary, but E normal, it jumps by sigma by epsilon naught if there is a sigma at the boundary. And the V is always continuous, but delta V by N, okay, in the perpendicular direction, jumps by minus sigma by epsilon naught. So with that, I come to the end of the chapter 2b, in which we have done the charge distribution, its relation to field, and from field to potential. Thank you.